When we talk about the NVIDIA H100, the conversation almost always centers on large language models and generative AI. It is often framed as a specialized machine for a single purpose. But looking under the hood reveals a more versatile reality. The Tensor Core, the primary engine of the H100, is not just an AI button. It is a fundamental shift in how we process numerical data at scale. While traditional CPU cores handle instructions one by one, and standard GPU CUDA cores handle vectors, the Tensor Core operates on entire matrices in a single clock cycle. This capability, originally designed to speed up the dot products in neural networks, is now being hijacked by scientists, financial analysts, and engineers for tasks that have nothing to do with machine learning. Today, we explore why the H100 is becoming the backbone of all high-performance computing. To understand why Tensor Cores are so versatile, we have to look at the math. At their heart, they perform a specific operation, D equals A times B plus C. In the world of computing, this is a fused multiply-add, but Tensor Cores do it for 4x4 or 8x8 matrices instead of individual numbers. This matrix-matrix multiply accumulate is the common denominator of almost all heavy numerical workloads. Whether you are calculating the stress on an airplane wing, simulating weather patterns, or processing radar signals, you are essentially performing massive amounts of linear algebra. By baking the ability to multiply matrices directly into the hardware logic, NVIDIA has created a shortcut for any problem that can be represented as a grid of numbers. It's the difference between painting a wall with a tiny brush versus a massive industrial roller.
A common misconception is that Tensor Cores only handle low-precision math like FP16 or int8, which are great for AI but terrible for science. The H100 shatters this limitation. It introduces the fourth-generation Tensor Core, which supports a massive range of data types. For AI, it uses FP8 to double throughput. But for scientific research, it supports FP64, double precision floating point. This is the gold standard for simulations, where tiny rounding errors can lead to a bridge collapsing or a rocket missing its orbit. Additionally, the H100 supports TF32, or TensorFloat32. This format provides the range of standard FP32 with the speed of a Tensor Core, requiring zero code changes for many existing applications. This flexibility makes the H100 a chameleon of compute, adapting its mathematical engine to the specific needs of the problem.
Let's look at a concrete non-AI example, computational fluid dynamics. When an engineer simulates air flowing over a car, they divide the space into millions of tiny cells. Each cell's state depends on its neighbors, creating a massive system of linear equations. Traditionally, these were solved on CPU clusters over days. With H100 Tensor Cores, these solvers can be accelerated by an order of magnitude. By mapping the stiffness matrix of the physical system onto the Tensor Core's MMA hardware, we get results in hours instead of days. This acceleration enables interactive design, where engineers can tweak a 3D model and see the aerodynamic impact almost instantly. This isn't AI, it's classical physics supercharged by hardware that was originally meant for cat pictures. Another massive field is digital signal processing, or DSP. If you've ever wondered how 5G towers handle thousands of simultaneous connections, the answer is the fast Fourier transform, or FFT. FFTs are the mathematical foundation of wireless communication, medical imaging like MRIs, and even oil exploration. While dedicated DSP chips have existed for decades, they lack the raw scale of an H100. Modern libraries like QFFT can now offload the most intensive parts of these transforms to Tensor Cores. By treating the signal data as a matrix, the H100 can process terabytes of radio frequency data in real time. This allows for more precise beamforming in telecommunications and clearer images in diagnostic medicine, proving that the H100 is just as much a radio engine as it is an AI engine. Finally, we see Tensor Cores transforming data science and databases. In the modern era, we don't just search for keywords, we search for meaning using vector embeddings. This is how Netflix recommends movies, or how a vector database finds similar images. Comparing a search query to billions of database records is essentially a massive matrix vector multiplication. By using tensor cores to calculate these cosine similarities or Euclidean distances, databases can search through billions of items in milliseconds. This isn't just about speed, it's about the scale of what's possible. We are moving from a world where we search for exact matches to a world where we can instantly find patterns across the entire sum of a company's data. The H100 represents a turning point in architecture. It is the first chip where the distinction between AI hardware and general-purpose hardware starts to disappear. As software developers and scientists, the takeaway is clear. If your problem can be represented as a matrix, the H100 is your most powerful tool, regardless of whether there's a neural network in sight. We are entering the era of multi-precision compute, where the same chip that generates your favorite AI images is also predicting the next hurricane and securing our communication networks. The Tensor Core is no longer just for AI, it is for everyone. Thanks for watching.